In Chapter 8, what we're going to be working on is testing the difference between means when there's more than one sample. So in Chapter 7, we were testing hypothesis for the population mean, standard deviation, variance, proportion, and in Chapter 8, we're going to be looking at the difference between the means of two different samples. So let's get a little bit of information going. In Section 8.1, we're going to be talking about samples that are independent of one another, and also samples when sigma 1 and sigma 2 are known. So we have two different populations that are independent, and we know the standard deviation from each population. So in these, what we are doing is comparing parameters. In this case, it's going to be mu for mean from two populations instead of just one population. So let's talk about the difference between independent samples and dependent samples. In Section 1, we're going to be dealing with independent samples. In future sections, we'll be testing for dependent samples, so we need to know the difference. So independent samples means that the sample from one population is not related to the sample from the other population. So we have sample 1, sample 2. And in sample 1, we have all of our different data values in there. And sample 2, we have different data values in there. But there's no overlap between the two samples. So sample 1 might be 18 to 25-year-old males. And sample 2 might be 18 to 25-year-old females. So what we're going to do when we test the difference between means is we're going to say, okay, so what is the mean age at which, or maybe the mean income for 18 to 25-year-old males, and we want to see if it's the same or different from the mean income for 18 to 25-year-old females. So these would be independent samples because they don't overlap. But then we can also have dependent samples. And a dependent samples can also be called matched samples or paired samples. So in this instance, we have sample 1 and sample 2. And each piece of data in sample 1 would correspond to a piece of data in sample 2. So every time I have data in sample 1, it matches up with another data value in sample 2. Not meaning that they're the same number, just meaning that they correspond to one another. For example, if we had 25 students in weights class, and sample 1 could be those same 25 students. So sample 1 could be 25 students in weights class. Sample 2 could be those same 25 students 6 months later. So what we could be comparing between our two samples is what's the average bench press in this sample of 25 students, and then we match up each data value with the same student 6 months later, and we want to see, are those averages the same or are they different? So in a dependent sample, which is also called matched samples or paired samples, each member or data value of one sample corresponds to a member from the other sample. So let's look at some examples and decide whether our samples are dependent or independent. So we're supposed to classify the two samples as independent or dependent and explain your reasoning. We might just explain it verbally and not write it down. So sample 1 has the maximum bench press weights for 53 football players. Sample 2, the maximum bench press weights for the same 53 football players after completing a weightlifting program. So those two samples would be dependent because they are using the same people in sample 1 as they do in sample 2. So I would match up player number 1 before the weights class with player number 1 after the weights class, and then that's what makes those dependent. Number 6, sample 1 is the IQ scores of 60 females, sample 2 the IQ scores of 60 males. So the 60 females and the 60 males, even though there are 60 of them, they are going to be independent samples because they don't match up with one another. So those are independent. We would want to be looking at the average IQ for females versus the average IQ for males, not comparing them for progress purposes like we did in number 5. Number 7, the average speed of 23 powerboats using an old hull design compared with the average speed of 14 powerboats using a new hull design. So these are 23 powerboats and this is 14 different powerboats, so those two samples would be independent. Number 8, we have the commute times of 10 workers when they use their own vehicles versus the commute times of the same 10 workers when they use public transportation. So these are the same 10 people, so these are dependent samples. Let's talk about claims because we are going to be doing hypothesis testing. So we need to figure out how to state claims. So claims. The claims in this case are for comparing two means. So they're not going to have numerical values. They are going to be saying like the first mean is equal to the second mean, or the first mean is bigger than the second mean, etc. So the claims are for comparing two means, not for finding values of the means. So we're going to have 3 possible types of claims. In type 1, the null hypothesis is that mean number 1 is equal to mean number 2. So this is population mean 1 is equal to population mean 2. And then our alternative hypothesis would be that they are not equal. So that's going to give us a two-tailed test when we go to make our rejection region. Another option is for the null hypothesis to be that mean number 1 is greater than or equal to the mean for population 2. Then the alternative hypothesis would be mean 1 is less than mean 2. So that would give you a left-tailed test. The third possibility is for the null hypothesis to be mean 1 is less than or equal to mean 2. And the alternative hypothesis would be mean 1 is greater than mean 2. And then this would be a right-tailed test. It doesn't matter which hypothesis you use, regardless of which of these three. I mean, it matters to the problem, but regardless of which of the three you use, regardless of which hypothesis is used, we always start our testing by assuming that there is no difference between the two population means. So the two population means are mu1 and mu2. So regardless of which testing we do, we assume that there is no difference between the population means, mu1 and mu2, when doing the testing. So when you do your testing, you assume that mu1 is equal to mu2. And you'll see how that's going to come into play here when we write out the steps. So here are going to be the steps for hypothesis testing. So this is a 2 sample, and we are going to be using a z-test for this type of hypothesis testing for the difference between two means. And just like in chapter 7, when we're doing hypothesis testing for means with a z-test, that means that we know sigma. So this is going to be for independent samples when sigma is known. So the first step, we have some things to verify. We need to verify that sigma 1 and sigma 2 are known. We also need to know that our samples are randomly selected and they are independent. And then we need to know either that populations are normally distributed or the sample size is bigger than the magic number of 30. So or N1 is greater than or equal to 30 and N2 is greater than or equal to 30. Step 2 is going to be to state H sub 0 and H sub A, identify which one is the claim, and determine your level of significance, alpha. Just like we have in the past. Step 3. Determine the critical values, just like we did in previous chapters. So determine the critical values, and then we're going to sketch and shade the rejection region, or regions if it's a two-tailed test. And then we find the standardized test statistic. In this case, it's going to be a z-score. This is kind of a big formula, so I'm going to write it somewhat large. So z is going to equal, it's x bar 1 minus x bar 2. Subtract from that mu 1 minus mu 2. And then we divide by this big square root. The big square root has sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. So let's label what some of these things are. This mu 1 minus mu 2, that's the hypothesized difference between the means. And if you remember from up here, regardless of which hypothesis is used, we always assume there's no difference between the means. So we're assuming mu 1 is equal to mu 2. So this equals 0. We always assume mu 1 equals mu 2. So this equals 0. This over here is the observed differences between the means, and it's based on the sample means. So we're using x bar 1 minus x bar 2. And then in the denominators we have the standard deviation for the first sample, for the first population, divided by the sample size, plus the standard deviation for the second population divided by the sample size, and it's the square root of that whole mess. Then the fifth step is, once we have that standardized test statistic, we're going to decide based on rejection regions whether we reject H sub 0 or do not reject H sub 0. And then the last thing we're going to do is interpret the decision in context of the original claim. And that goes with that table that we used in 7.1, where it depends on which one is your claim. I'll get that right here. There's our interpretation chart. So if you want to pause that and recopy it, you certainly may. But I am going to move on and do an example going through all those steps. It's about spending more time sleeping. A sociologist claims that children ages 12 to 14 spent less time sleeping in 1981 than children ages 12 to 14 do today. A study was conducted in 1981 to find the time that children ages 12 to 14 spent sleeping on weekdays. The results in hours per weekday are shown below. Assume the population standard deviation is 0.5 hours. So here's our 1981 data. Recently, a similar study was conducted. The results are shown below. Assume population standard deviation is 0.4 hours. Here's that data. At alpha equals 0.01, can you support the sociologist's claim? So, here's the claim. Claims that children spend less time sleeping in 1981 than children do today. So we're going to make our first population be 1981, and our second one is going to be now. So this right here, this is going to be sigma 1 equals 0.5. And then for N1, the number in our sample, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 20. N1 is 20. And then our second population is going to be now instead of 1981. So we have population standard deviation is 0.4 hours. So sigma 2 is 0.4 and N2 is also 20. There's our alpha. And we need to figure out what our claim is. So according to our steps, the first thing we need to do is verify that sigma 1 and sigma 2 are known, which they are, and that the samples are randomly selected. Yep. We'll assume they were randomly selected. The important part about the verify is that sigma 1 and sigma 2 are known and the samples are independent. So these are children who were ages 12 to 14 in 1981, and these are children who are ages 12 to 14 recently. So these are not going to be the same kids, so we have an independent test. So the next thing on our list is to state H sub 0 and H sub A. So H sub 0, H sub A, and identify which is the claim. Well, the claim is that children in 1981 spent less time sleeping than children do today. So we've got that children in 1981, which would be population 1, is less than now, which is population 2. So what they're saying is that the average time sleeping, mu1, is less than the average time sleeping recently. So this right here is our claim, is that they spent less time sleeping in 1981 than they do today. So that's mean number 1 is less than mean number 2. Since that's our claim, then H sub 0 would be mu1 is greater than or equal to mu2. After we've stated those, our level of significance was alpha. We need to determine our critical values, sketch and shade the rejection region. So since H sub A is a less than, then our test will be a left-tailed test. And when alpha is 0.01, that means this area is 0.0100. So we're going to look that critical value up in our standard normal distribution. So 0.0100. I can do this. Right there, that's the closest one. So our critical value will be negative 2.33. And we're next going to find our standardized test statistic. So that's going to be a z-score. So I'm going to write down that formula. Z equals x bar 1 minus x bar 2 minus mu1 minus mu2 divided by square root sigma squared 1 n1 plus sigma 2 squared n2. To find x bar 1 and x bar 2, what we need to do is find the mean of our samples, because these are sample means. So this is the sample mean for this data right here. And we would do that by putting our data in our calculator. So I would need to type all those in. Okay, and then stat calc one variable statistics, and I want list 2. So that's telling me that my mean is 7.75. So X bar 1 is 7.75. And then I already typed in the data for the other set. So I need to calculate one variable statistics for list 1. And my mean is 8.99. And then remember that mu1 minus mu2, the assumption we make is that these two are the same, so that value is always 0. And then we're going to divide by. In our problem, we're given the standard deviation. However, this is the variance. So we're going to take our standard deviation of 0.5 and we square it. And then divide by n1, which was 20, plus, same thing here, this is standard deviation, the formula wants that to be squared, so 0.4 squared, also divide by 20. And from here, it's just super careful calculator work. So I'm going to take 7.75 minus 8.99. That's negative 1.24 divided by square root of 0.5 squared divided by 20 plus 0.4 squared divided by 20. So that's going to give me a z-score of negative 1.24 divided by that number. Negative, oh, I forgot to square root that number. Negative 1.24 divided by the square root of that number. There we go. Negative 8.66. So that's my standardized test statistic from step 4. On step 5, I get to decide whether to reject or not. Well, my z-score is negative 8.66, which is going to place it over here, way off to the left, which is in the shaded region. So since it's in the shaded region, we reject the shady hoe. So we are going to choose to reject H sub 0. Now, back to our table. H sub A was our claim, and we're rejecting H sub 0. So H sub A is our claim, and we're rejecting H sub 0. So we would want to use this statement. There is enough evidence to support the claim that blank. So we are going to say at the, if alpha is 0.01, it's a 1% level of significance. There is enough evidence to support the claim. Well, the claim was that children ages 12 to 14 spent less time sleeping in 1981 than they do today. So that's the claim. The claim that 12 to 14-year-olds in 1981 spent less time sleeping than they do today.